In this lesson, we will evaluate some trigonometric integrals which, before we evaluate them, require manipulating the integrand using some trig identities. So first, let's review some stuff from Calculus 1. So integrate the following functions using a u-substitution. So for this particular integral, if we let u equal sine of x, then du is equal to cosine x dx. And this becomes the integral of u to the fifth du, which is 1/6 u to the sixth plus c, or 1/6 sine to the sixth x plus c. And what you should notice there is what we really needed for this to work is we needed this cosine of x that ended up taking care of the du. Alright, now in this next one, what you can notice is if you let u equal tangent x, du is equal to secant squared x dx. So this becomes the integral of u to the seventh du, or 1/8 u to the eighth plus c, which is 1/8 tangent to the eighth x plus c. And in this particular example, we had to have a secant squared there to take care of the du. What we're going to need for many of today's examples are the following Pythagorean identities. You should have learned these in pre-calculus. Just as a quick review, once you know this one, all the rest of them are consequences of it. If you take the first identity and divide everything by cosine squared x, that gives you sine squared x over cosine squared x plus cosine squared x over cosine squared x equals 1 over cosine squared x. Sine squared over cosine squared is tangent squared, plus 1 equals 1 over cosine squared x is secant squared x. And then you can guess that to get the last one, what you do is you divide the original identity by cosecant squared x. And after you do that, that more or less falls out. Alright, evaluate the integral of cosine cubed x. Well, we can't let u equal cosine because the derivative of cosine is negative sine and there's no sine to be seen. So what we can do is this, we're going to manipulate the integrand using those identities. So first notice that cosine cubed x is cosine squared x times cosine x dx. And then, since sine squared x plus cosine squared x is equal to 1, this cosine squared is 1 minus sine squared. And now, if you let u equal sine, you can just use a u-substitution to find this integral. So u is equal to sine x, du is negative cosine of x dx. So we just have plain old cosine of x, so we will have to use negative du. And this becomes negative integral 1 minus u squared du, or negative u minus 1/3 u cubed plus c, or we insert u, negative sine of x plus 1/3 sine cubed x plus c. And you'll notice two things that you have to have happen here. First of all, you have to save a single cosine to be part of your du, and the other thing that has to occur is the powers have to be even in order to use those identities. So let's try another example. So sine to the fifth x times cosine squared x. Now we can't break up cosine squared x because that gives you an odd power on a cosine, and there's no identity for odd powers that using right now. So instead, let's take the sine, and we'll manipulate that and write that as sine to the 4th x, and then cosine squared x times the single lode sine x dx. And then notice that sine to the 4th x is the same thing as sine squared x squared. And now what you can do is use your identity to change these into cosines, and then you can u-substitute for cosine. So sine squared x is 1 minus cosine squared x. And now if we let u equal cosine of x, du is negative sine x dx. So negative du equals sine x dx. So this becomes negative the integral 1 minus u squared, the quantity squared, times u squared du. And now we have to expand that integral, so that would be 1 minus 2u squared plus u to the 4th times u squared du, or negative integral u squared minus 2u to the 4th plus u to the 6th du. And now when we antidifferentiate and reinsert our u, we end up with negative 1/3 cosine cubed x plus 2/5 cosine to the 5th x minus 1/7 cosine to the 7th x plus c. So in general, if the power on a sine or a cosine is odd, what you do is you leave behind one of these sine or cosines and use the Pythagorean identities to transform the integrand, so you make your u-substitution for one of the trig functions. Next, let's consider what happens if we only have a sine or cosine to an even power. So for these, we're going to use the half-angle identities. Now, most pre-calculus classes don't show them to you in this form. What they show them to you like this. So that's the same thing as 2 sine squared x equals 1 minus cosine of 2x, or 2 sine squared x minus 1 equals negative cosine 2x, or cosine of 2x equals 1 minus 2 sine squared x. So usually you probably have seen them in this form. The way we're going to use them is where they are solved for sine squared and cosine squared. So we have the integral from 0 to pi of sine squared x. So we know that we can rewrite sine squared x as 1/2 times 1 minus cosine of 2x, 0 to pi. So let's take out the 1/2, and we have the integral from 0 to pi of 1 minus cosine 2x. So the antiderivative of 1 is just x. Now the antiderivative of cosine is sine. So we'll have sine of 2x, and just think for a second what you need there to make it so that this function differentiates to this one. So sine of 2x's derivative is cosine of 2x times 2, which means you need a 1/2 there. If you're uncomfortable with that, you can do a u-substitution for the 2x, but this is just a lot easier. Evaluated from 0 to pi. So that gives us 1/2 times pi minus 1/2 sine of 2 pi minus 1/2 times 0 minus 1/2 sine of 0. So sine of 2 pi is 0, sine of 0 is 0, and this is just equal to pi over 2. So the area under the sine squared curve between 0 and pi is pi over 2. Next, suppose we have a trig function raised to a power that's greater than 2. What you can do here is notice that sine to the 4th x is equal to sine squared x squared. And sine squared x is equal to 1/2 1 minus cosine of 2x. And we're going to square that instead. Now, the 1/2 squared becomes 1/4. When we square the 1 minus cosine of 2x, we end up with 1 minus 2 cosine of 2x plus cosine squared 2x. Now, this part's okay, that part we can handle. This part, we're going to apply the half angle identity again. And instead of plugging in x, we plug in 2x. So we have 1/4, the integral of 1 minus 2 cosine of 2x plus 1/2 times 1 plus cosine of 2 times 2x. Now, that gives us 1/4 integral of 3 over 2. Now that comes from adding this 1 to, this is a 1/2 once that 1/2 is distributed, minus 2 cosine of 2x plus 1/2 cosine of 4x. Now the antiderivative of 3/2 will be 3/2 x. The antiderivative of cosine will be sine of 2x. And just check, if I differentiate sine of 2x, I end up with cosine of 2x times 2, so we're good to go there, plus 1/2 times 1/4 sine 4x plus c. So the final answer is 1/4 3/2 x minus sine of 2x plus 1/8 sine of 4x plus c. Alright, find the integral of 2 plus sine of theta, the quantity squared. So the first thing that I can think of doing here is expanding. So I'm multiplying 2 plus sine of theta by itself, and that gives us 4 plus 4 sine theta plus sine squared theta. And the first two terms we can integrate just fine, but we have to convert this sine squared theta using the half angle identities. So that will give us the integral of 4 plus 4 sine theta plus 1/2 times 1 minus cosine of 2 theta d theta. Now that gives us, when we add the 4 to that 1/2, we have 9/2 plus 4 sine theta minus 1/2 cosine 2 theta. Now the antiderivative of 9/2 is 9/2 theta. The antiderivative of sine is negative cosine, so we'll end up with minus 4 cosine of theta minus 1/2. The antiderivative of cosine is sine of 2 theta, and then times 1/2 plus c. So that gives us 9/2 theta minus 4 cosine of theta minus 1/4 sine of 2 theta plus c. Now for this next example, this one will be similar to the second example that we went over where we sort of reviewed some Calculus 1 u-substitutions. So if you want to u-substitute for tangent, the derivative of tangent is secant squared. So first we take this integral and we break it up into tangent to the 6th x, secant squared x, secant squared x dx. Now we save one of those secant squares to be the du. If we're going to let u equal tan x, du is secant squared x dx. And using the Pythagorean identities, we can manipulate secant squared x into tangent squared x plus 1. So you have the integral of tangent to the 6th x times tangent squared x plus 1 multiplied by secant squared x dx. And now we make our u substitution, and that gives us the integral of u to the 6th times u squared plus 1 du, which is the same thing as u to the 8th plus u to the 6th du, or 1/9 u to the 9th, so tangent to the 9th x, plus 1/7 tangent to 7th x plus c. And on this example, because the power on the secant was even, we could make this work. On this next one, if you try to save a secant squared so that you can u sub for tangent, you're going to end up with secant having an odd power. And then you can't use the Pythagorean identities to change secants into tangents. But what you can do instead is this: save both a tangent and a secant. So this becomes the integral of tangent to the 4th x, secant to the 6th x, times tan x secant x dx. And you remember, the function who has derivative tan x secant x is actually secant. So if we were able to let u equal secant of x, then du would equal secant x tan x dx. Now to do that, we have to change these tangents into secants. But that's completely doable. That is the same thing as tangent squared x squared and tangent squared x is equal to secant squared x minus 1 squared times secant to the 6th x tan x secant x dx. And when we do our substitution, this gives us the integral of u squared minus 1, the quantity squared, times u to the 6th du. And if we expand that out, we end up with u to the 4th minus 2u squared plus 1 times u to the 6th du, or the integral of u to the 10th minus 2u to the 8th plus u to the 6th du. And now anti-differentiate and plug back in what u was. We end up with 1/11 secant to the 11th of x minus 2/9 secant to the 9th x plus 1/7 secant to the 7th of x plus c. The last type of integrals that we are going to tackle involve integrands where a sine is multiplied by a cosine, or a cosine multiplied by a cosine, where the arguments inside the sine and cosine might be different values. So to handle those, we use these sum and difference formulas. Now these are not formulas that I would make you memorize, but you may have to look them up and use them on a homework problem of some sorts. So here we go. So we have the integral of sine of 4x times cosine of 5x. So for that, we will use the first formula, and that says that the integrand, this sine of 4x cosine 5x, is equal to 1/2 times sine of 4x minus 5x plus sine of 4x plus 5x. And this helps because all of a sudden you've taken a product and made it into a sum where you can evaluate each of the terms in the sum using a really easy u-substitution. So that's sine of negative x plus sine of 9x. And one kind of nice thing about sine, where that sine is an odd function, which means that sine of negative x is actually equal to negative sine of x. Okay, now we antidifferentiate. Now the antiderivative of sine is negative cosine, so we'd have negative cosine of x plus negative 1/9 cosine of 9x plus c, which is 1/2 times the quantity cosine of x minus 1/9 cosine of 9x plus c. Lastly, just a slight warning. If in your homework you come across a function where you end up with the integral of tangent or the integral of secant, you might want to use one of these formulas. Now, the integral of tangent is negative ln of cosine x plus c, or ln of secant x. If you want to figure out why that's true, you just have to notice that that tangent is equal to sine over cosine. That's the integral of sine x over cosine x dx. And if you do a u-substitution for cosine of x, you end up proving this formula. Now, secant x is a little bit less obvious. That's quite tricky. So how you evaluate the integral of secant x is you multiply by secant x plus tan x over secant x plus tan x. And that gives you the integral of secant squared x plus secant x tan x over secant x plus tan x dx. And then if you let u equal secant x plus tan x, the formula falls out. But that method, or this trick to integrate secant, is, well, rather tricky. So not something you would come up with on your own. So just be aware that that is the formula for the antiderivative of secant and the antiderivative of tangent, just in case you run across them.